Okay, this is going to be a short crash course in the information you need to know for the diprotic acid lab for this week. I realize that some of you may not have gotten to acids and bases just yet. Everyone has seen equilibrium. And this really has to do with treating acids and bases as a special kind of equilibrium reaction. If this content seems confusing, you may want to wait for the longer version of this. So when we have an acid and we dissolve it in water, as we would with hydrochloric acid or sulfuric acid, before we have anything dissolved, the hydrogen atom is bonded to the rest of the molecule. But after it dissociates, we have separate particles. So we have what we call the conjugate base listed here as A-, and that's everything but the hydrogen. The hydrogen attaches itself to a water molecule. And so you can see that as the red balls with 3 light blue balls attached to them. Now, in the case of a strong acid, like the ones that we work with in lab, hydrochloric acid, nitric acid, this is complete. And so there are no molecules left of HCl or HNO3. But what we find to be the case is that many acids are going to be weak acids. Now, before we get into weak acids, what I want to talk about is how we measure acidity. So we are going to look at the concentration of H3O+. This is the hydronium ion. Concentration is put in brackets. Remember that whatever the concentration of our strong acid is, that's going to be the concentration of the hydronium because it completely dissociates. We've got a list of our strong acids there. And so if we have 6 molar hydrochloric acid, then the concentration of hydronium is 6 molar. So what we want to do is we want to measure the pH of these things. pH stands for power of hydrogen. And it is the negative log of that concentration. So whatever the concentration works out to be, we take the log of it and then change the sign from negative to positive. So if I have 0.001 molar HCl, which is a strong acid, then my hydronium concentration is also 0.001, and I'd plug that into this formula and I'd get a pH of 3. Okay, so ultimately, in order to find the pH, we need to be able to get to this hydronium concentration. Notice that this 3 is a fairly low number. The lower the pH, the more concentrated the acid is. So very acidic would be 0 or 1, slightly acidic would be 5 or 6, and 7 is neutral. Okay, what about weak acids? With weak acids, when they are dissolved in water, they only dissociate partly, which means only a very small percentage, usually less than 1% of the molecules have the hydrogen separate out from the rest of the molecule. And so we have this similar picture over here with the A- in yellow and the H3O+ with the red ball and the 3 hydrogens attached to it. But we also have a lot of these green molecules, which is the molecular form of our weak acid. And so we can treat those like an equilibrium problem. So this is a problem that we could work through. It's not really relevant to our lab, but I am going to use HF as my example. So HF is hydrofluoric acid. So what this lab is about is titration. When we are titrating something, you've done this in lab before, you are adding a very precisely measured amount of one substance to another. So what we've done is we've titrated an acid. So we've had an acid in a beaker or a flask, and we've added from a burette the base. And because the burette is so precise, we can tell precisely how much we have added. So the one that we did last fall involved a strong acid and a strong base. And the one that we did this spring involving vinegar involved a weak acid and a weak base. So when we do this, it's kind of like disturbing an equilibrium the way that you talk about with Le Chatelier's principle. So if we look at this reaction of the weak acid of hydrofluoric acid in water, it's going to dissociate partly a very small percent, less than 1%, into the hydronium ion and the F- ion. As we add the NaOH, that NaOH is going to get together with the excess hydronium and they're going to form water molecules. So adding the base is going to remove the hydronium ion because it's combining, it's neutralizing to form the water. And since there's less of it, the pH is going to increase. And that's what we're going to be measuring. The equilibrium aspect of this is it's going to keep shifting the reaction forward. So we're going to use up our hydrofluoric acid as we do this. All right, so when we have an equal number of moles of the base added, OH minus ions, to the original amount of the initial amount of hydrofluoric acid, we have used up all of the HF, okay? This is what we call our equivalence point. At this point, the OH isn't reacting with HF anymore. It's going to start reacting with the water. So we have this equilibrium reaction between water. And so that kind of changes our story of what's going on. What we're interested in is what happens right up to this equivalence point. So we can make a graph of this. This is what you're going to be doing in lab. You're going to have a pH probe that will tell you the pH as you add different amounts of the NaOH. So a titration curve usually has a pH measured on the y-axis. Remember, 7 is neutral, and it has milliliters of whatever the titrant is. In this case, NaOH is going across the bottom. Remember that below a pH of 7, we have an acid. So on our litmus paper, that would turn pink. And above a pH of 7, we have a base. And our litmus paper, it would turn blue. So these are kind of the axes. Now, the red and the blue are going to go away, but we just kind of want to remember 7 is our neutral area. Back up a second. As you begin the titration, you're probably going to see a graph much like what you have on the left-hand side here. So notice we have the pH on the left, the y-axis. We have milliliters of the hydroxide being added. And we're going to start seeing something that looks like a line kind of going up. It may look like a straight line. It may look slightly curved. But notice that the top point here is at 3.5. So even though this looks like this is changing pretty dramatically here, if we look at it on a full scale graph where it goes from 0 to 14 like it does on this right-hand side here, that looks pretty flat. Okay, so the first part is going to be fairly flat. As we approach the equivalence point, you'll notice that this flat line starts to curve up. It's more dramatic here when we have it auto-scaled, and the graphical analysis sometimes will auto-scale, so you'll start to see it curving up, but you can also see it on the full scale. When that happens, the pH is changing very dramatically, and you want to add just a little bit at a time, just a few drops, because we're really interested in what's going on here near this equivalence point. As we get to the equivalence point, and this is right up to the equivalence point, notice how almost vertical this line is getting to be, all right? And that's how we're going to know where our equivalence point is. Now, remember when you were doing your titrations using phenolphthalein, that if you added a drop at this point, it might go from colorless to bright pink very rapidly, just with a drop or two of your base being added. And that's because the pH is changing so quickly. So we're below 7 at this point, but another drop or two may put us well above 7. Okay. And so if we go beyond that, this is adding even more and then continuing to add our base. we end up with kind of an S here. Okay, so what we are interested in looking at on this graph is the equivalence point. And the equivalence point is right here in this most vertical region, okay? And we are interested in what is that volume. So we're gonna take this line down to the x-axis and look at the volume here. So this is about 37 milliliters for our equivalence volume. And the reason we're interested in that is from there, we can get the number of moles of base we have added, okay? So we're interested in the volume of the base at the equivalence point. And the equivalence point is the most vertical region of this S graph. Okay, so at the equivalence point, moles of OH is equal to moles of HF. And we're interested in finding the moles of our acid. Now, this is moles, not the concentration. Okay, so they may have different concentrations. This is just the number of moles. So how do we find moles of OH? We use the molarity times the volume. So the molarity of the bottle, let's say it was 0.0988. Now, your molarity might be something slightly different. This one was 0.0988. Times the volume. So I have the volume as 0.0375 liters. So notice it's not 37 because on our graph, we're measuring milliliters. I need to convert that to liters. And so when I do that, liters times molarity, which is moles per liter, is going to give me moles. So this 0.00370, that is moles of hydroxide. And that is equal to the moles of our HF, which is what we're interested in. And that is the moles from the initial concentration. Because remember, when we get to the equivalence point, we've used it all up. So that it's not what's there at the equivalence point, it's what we started with. All right, so we might be trying to find a couple of different things. In the past, a titration, we were trying to find the concentration of the acid. So if we're trying to find the concentration, as indicated by the square brackets around this, what we would do is take that number of moles and divide by the initial volume of the acid that we added. This lab is a little bit different. We're using a solid acid. And so that solid, we're not going to worry about the volume. We're just going to add the solid knowing the mass. And we're going to try and find the molar mass. So remember, molar mass is grams per mole. So we're going to take the grams of the acid that we add, that's the mass, divide by the moles as determined from this process. Okay, so molar weight is mass divided by moles. All right, so this is what we would call a monoprotic acid. A lot of weak acids are monoprotic. It's a very simple titration curve, just looks like a basic S. But in this lab, we're looking at a diprotic acid. Oh, before we get to the diprotic acid, there are some other things we can tell from here. So notice that we have this long flat region, and we might think, well, that's not interesting. We don't really care about that. But that's actually something that we can make use of. That region is what we call the buffering region. And so a buffer is something that it doesn't change its pH a whole lot when you add an acid or a base. So you can see here, we've added 10 or 15 milliliters of hydroxide and the pH has barely changed. And so we can also use this to find some important information about the acid. If we look at half the equivalence volume, so remember the equivalence volume was right about 37, we're going to look at half of that. So that's going to be our about 18.5. At half that volume, the pH is going to be equal to the pKa. So we draw in tie lines coming up from this volume up to where the graph is. And you might need to sketch in where that line is so that you can see it. And then over to the y-axis, this pH here, which is about 3.5-ish, that's equal to the pKa. Okay, so that's something you're supposed to find in your lab. What does pKa mean? Very briefly, it is taking the Ka, the equivalence, the equilibrium constant, K, and doing the same thing we did with the hydronium, negative log of that. So this is what it should be for HF, 3.46, or very close to 3.5. Longer version will be in a different video. With diprotic acids, this means that we have more than one ionizable hydrogen, more than one hydrogen that can come off as an H+. When this happens, they don't both come off at the same time. They come off first, the first one on all of the molecules, and then the second one. So all of the first hydrogen is removed before any molecules start removing the second hydrogen. Now that's a generalization that's not exactly true, but it works for our purposes. So some examples of diprotic acids are over here. So we have sulfurous acid. It's got the H2 out front, but a lot of the weak acids that we will see are going to have this COOH group. That is a carboxylic acid. It's an organic acid. And so you'll notice that each of the three listed here have that in parentheses with a 2 after it. And that indicates there's 2 of those groups on that molecule. So the first one is oxalic acid, then malic acid, which is found in apples, and maleic acid. Those are examples of diprotic acids. So ideally, you would have a curve that looks something like this with the diprotic acid. And it kind of looks like I've put 2 of those S curves together. So the first S curve over here on the right is showing me my first equivalence point. That is where I've lost all of my first hydrogen, but I haven't really lost any of my second hydrogen yet. My second equivalent point is where I have lost both of the hydrogens. Lost all of the hydrogens that are ionizable. Okay, so we have 2 equivalence points for a diprotic acid. Now take a look at the volumes for these. So we were interested in the volume at the equivalence point. The volume at our second equivalence point here is a little above 20, maybe not quite to 21. And the volume at my first equivalence point is right about half that, just a little over 10. And this is what we should find, is the first equivalence point volume is half of the second equivalence point volume. All right, so at the first equivalence point, all of what we said about a monoprotic acid is true. The moles of OH is equal to the moles of the acid. And we can find the moles of OH by doing the molarity of the NaOH times the volume that we've added, the volume from the burette. And then if we wanted to find the molar weight, as we are in this lab, we just take the mass that we measured out, divided by the moles of the acid, which is equal to the moles of the OH. So we just take mass divided by moles. At the second equivalence point, which is sometimes a little easier to see, we have twice as many moles of hydroxide as we do of acid. So we had to use 2 moles of hydroxide for every 1 mole of the acid in order to get to our second equivalence point. Finding the molarity of the hydroxide is still the same because its concentration didn't change. Okay, so we're still going to take the concentration on the bottle times the volume that we added. But the molar weight, which is the mass divided by moles of our acid, is going to be mass divided by half the moles of the OH that we've added. All right, so in this lab, as I mentioned, you're going to be finding Ka, but there are 2 Kas, one for the first ionization and one for the second ionization. So what we'll do is we will look at the equivalence point. And if we look at our first equivalence point, halfway back from that, so our first equivalence point we said was just above 10, halfway back from that is just above 5. We draw a line up to where it connects with the curve and then over to the side. So our first pKa should be just above 2. And then for our second one, we want halfway between our 2 equivalence points. So we're not going to take half of the second equivalence points. We're going to take 3/4 of that. So what you can do is find the average between the two. That's a good place to go. Or you can take the volume of the second equivalence point times 3/4. Either way, you should end up with, in this case, just above 15. Draw that up to the curve. Moving over from the curve to the pH, we can see this pKa2 should be just below 6. All right, so that's the quick and dirty how to find what you need to find for the lab this week. Good luck.